Hello, hello. So glad you could make it. Take a seat, get comfy, because we're about to go on a wild ride through the depths of Ruby pattern matching to explore some novel usages and new ideas in the form of playing a game of poker. But first, who am I? Well, simply put, my name is Brandon. I work at Square, and I like doing all manner of fun things to Ruby, hence this talk. You can find my Twitter in the bottom left of most slides, which will also have resources for the talk and other fun information if you want to read or find out more. In the meantime, though, shall we go ahead and get started? Now, we're going to start with a short preview into pattern matching and what it looks like, just to give you a glimpse of what we're going to be working with here today. Now, the following code may have been common in older versions of Ruby, but in 3.0, we introduced a new syntax, pattern matching. It looks a little something like this. It compares every value using triple equals and can use either array-like or hash-like strategies for pattern matching. Now, in the case of this talk, we'll be looking a lot at array-like matching, but what exactly is it doing? It's comparing each one of those elements positionally. The first should be an integer, the second should be a 2, and the third should just be there, using underscore as a placeholder for any value. Now, granted, this also captures nil, making it not 100% a match, but it does serve the point. Interestingly enough, there's a new experimental feature called one-line pattern matching, which I'll be using heavily in this talk, which may or may not make it into future versions of Ruby. Personally, I like the succinctness of one-line pattern matching to express this in a more concise way, and I certainly hope that it gets merged officially because I have all types of fun with it. Anyway, I like lemurs, and lemurs like games. In this particular case, they figured out how to play poker, but are horrid at scoring games, so they asked us to step in and use pattern matching to do just that. Convoluted, well, perhaps, but it's fun nonetheless. Now, to start out with, we're going to need to set up some structure for our game, like, let's say, some cards or a hand. Now, let's start out with a single playing card. We start with a new class to describe our card. And the first thing that I like to do with classes is I like to add some constants to describe the data inside that class. Now let's start with suits. S for spades, H for hearts, D for diamonds, and C for clubs. Now, while we could use the Unicode symbols for each of these, it's a bit quicker in REPL to use just the letters and type them out, because honestly, I can't ever quite remember those. Next, we're going to want to do something about ranks. Now, ranks go up from 2 to ace or ace to king, depending on your interpretation. For ranking purposes, though, we prefer this order. We also want all of them to be strings, so that we don't have to do any coursing downstream. We also want to give them a numerical index so we can reference them and find out what score is associated with each rank. While we could use some form of find index here, this is quicker for runtime and is referenced later as a constant for that purpose. Now what we're doing here is using each with index, which will take each of those numbers, or ranks rather, it will zip them with the index and they'll convert that to a hash, meaning that 2 would point to 0, 3 would point to 1, and so forth. Now that leaves us with a few constants to define the data of our class. Next, we want to actually make our card. And a card is a combination of a suit like spades and a rank like ace. We also want to give that an attribute reader, that way we can actually see those values. Now, let's do the same for a hand, which is a collection of many cards. We'll start out by defining constants again in our new hand class. To start out with, we want to know the order of types of hands and what their scores are. In the case of a royal flush is the highest and high card is lowest. We'll get into what each of those are in a little bit, though normally I'd use multiple lines here, and I do in the actual example code. We've condensed this a slight bit and put multiple on one line just for the sake of slide room. Now then, after we have those scores as a list, we want to take them backwards, giving us high to low, and merge them with their indexes using reverse each dot with index. We can pass 1 to start the indexes at 1, meaning that royal flush will be paired to 10 points, all the way down to high card, which will be paired to 1 point. The score map inverts those to where 10 points points to royal flush, 1 point points to high card. This will also be useful later in some of our testing code. Now, let's take a look at how our hand is actually constructed. A hand is a container of cards, which means that we take any number of cards in here. We could limit this, but for the sake of this, we'll rely on simplicity. I'll leave that to an exercise of the viewer. Now, you might notice something interesting here. I'm calling sort on cards. That's going to be very, very important for later, but we'll leave it there for now. Sufficient to say pattern matching is very order dependent in the case of array-like matches, so the order in which our cards are presented is extremely important to make this work well. Now, we're also going to want some niceties to make it easier to create cards and hands and view them in either presentation for debugging or just to play around with and see what we have. To start with, let's talk about viewing cards. Now, back to our card class, we start with an array bracket method on self as an effective alias for new. You might notice the triple dot here. That is a new argument forwarding syntax which says take all the arguments that are given to this function and pass them right on to the next function, which is very useful for some of these alias-like methods, or for anything that acts as effectively a proxy. Now, why do we do this? Well, to emulate the behavior of struct, in which you can create a new version of a class using brackets. You might also notice the equals here, which is the new Ruby one-liner method. We'll be using both of these new features extensively throughout the talk. Now, back to our card. We also want to be able to represent them as either a string or an array. Nothing too exciting here, except we're using one-line methods again for quick definitions. You might notice we have parens. That's because they're required if there's no argument, hence their presence here for one-line methods. So if we had a card, the output of those might look something like this, where the string version is just S2 and the array version is S and 2. So back to our card again. There's one interesting method that allows us to do pattern matching, and that method is called deconstruct. It's a hook for pattern matching that tells our class how to match against an array-like pattern by pulling values out of the class and matching them. Oftentimes, 2a or 2ary or each or any of the enumerable-like methods are a great place to start, but some classes might be different. They might have other ideas on how that should work. But in general, a good rule of thumb is to take a look at 2a first and see if that fits your use case. Next up, we want some nice methods for creating cards. So looking at our card class again, we can define another method called fromString to represent importing from a string. Now, while I could type out all the extra brackets or new, this allows us to seriously condense things into passing just the string variant of card without really losing too much of the expressiveness of it. In this case, the first character is the suit, and the remaining are the rank. Now, you might wonder why I'm not just using the second character and why I'm using 1 dot dot. Well, that's because there are ranks like 10, which are going to break that. 1 dot dot is another newish feature, which I believe is in Ruby 2.7, which is an endless range, which represents 1 to effectively infinity. In this case, we don't have to type in -1 and say from the beginning to the end of the list or from the second character to the end of the list. Now, let's say we have an ace of spades here. That would translate into this. Next, we're going to want some similar view methods for our hands. Now, let's take a look at our hand class. We start with a similar bracket constructor just in case we happen to need it. But in this case, we're using cards and using splat on that to pass all the cards as singular entities. But you can see this gets a bit long, hence our earlier fromString method, and you can guess what's about to happen fairly soon here as well. But to start with, let's go back to our hand and some more of these display methods. We also want string and array representations, as well as a pattern matching hook to take a look at the representation of our hands. In this case, we want to take all the cards, turn them into strings like SA or HA or HK, and we want to join them together with commas. In the case of an array, we just want to expose the cards themselves. The same with deconstruct. If we're trying to match against a hand, we want to match against cards. Now that brings us to creating a hand. Back to our hand class, we want a similar from string method here, but it can be a bit more involved. We want to split the input string on either a comma or spaces so we have multiple accepted formats here, and then we want to make them all into cards. You might notice the _1 here, which is a numbered param, also fairly recent in Ruby. That's the implied first argument, allowing us to pass whatever items we split through to map and make new cards out of them. Now, back to our method here, we can give this a few tries. And if we run that and we put them back to a string format, we end up with something like this. You'll also notice in the case of the second one, it's sorted, which is very nice. Also very necessary, and we will get into that a little bit more later. Now, speaking of sorting, we should probably figure out how cards are sorted as well, because that is one of the crucial parts of this entire thing working. We'll start out with precedence, or how important each card is in relation to others, or rank. So back to our card class, we want to start by including comparable. Now, comparable is kind of like enumerable, except it allows us to compare things instead of enumerate over them for sorting and comparing values. And it comes along with a lot of nice interface methods as well, like sort, max, min, and other things in that neighborhood. But before we can define the interface method, we need to find out what the precedence of each card is. We can use the scores of each rank we defined earlier to do exactly this. Some games are different in that they use a suit as well, but this isn't quite one of them for the example we're using here. If we happen to change precedence, we could always make a new card that actually takes suit into account, but not for this one. Now, the interface for comparable uses this lovely rocket ship operator to work. It takes another instance, and we can use each card's precedence to help decide which is higher, lower, or perhaps even the same. Now, how exactly does that work? Let's take a look at some of these examples here. In the first case, we have the left card being greater, giving us back 1. In the second case, they have the same rank, giving us back 0. And in the third case, the card on the right has a higher precedence, meaning that it returns back -1. This is how the rocket ship operator works. Now, taken another way, we can take a look at these as an array that we happen to sort, and we get sort for free by using this interface, which tells us what exactly the cards need to be and how ordered. So this would end up giving us back something like this, where you'll notice that the rank is increasing as we go. Now onto the hand itself. Remember that sort method? Turns out there was a lot hidden in there. So if we were to take this hand, it's sorted in order for us so that we match against it. Pattern matching, again, relies heavily on order, and having consistent order reduces our potential match cases substantially, so we can express things much more clearly, especially for array-like matches. Now then, let's get into something fun. We have all these cards in hands, but we haven't exactly gotten into ranking and scoring them yet. Let's go ahead and do that now. So to start out with, we want examples. And examples are always useful to test against, and you can find these on the resource page as well. You might notice we're using the from string method here. Imagine what would happen if we used .new or the bracket accessor. While there's a good for brief use cases, this is far more succinct for describing a hand very quickly, and you do not lose much of the expressive value by doing this. It also fits a lot better on slides, but don't tell them that. So our first hand is Royal Flush, which consists of cards of all the same suit, and the cards rank 10 to ace, all present. We can define a method on our hand to take care of this. Let's add a comment real quick just to see what exactly we're after, to remind ourselves of what we're trying to match against. Now, what we're going to do for each of these is we're going to define a predicate method, or a method that ends in a question mark, to express the idea of whether or not something is a royal flush. To do this, we're going to take our cards and we're going to match them against a certain pattern. The pattern starts out with card brackets, which, for reference, comes with or without that method actually defined in the earlier class. You could do this with any Ruby class in existence right now, and this would still work. Now, this is very important to remember. Suit there. That's interesting. What exactly is suit? Because we haven't defined a suit variable anywhere inside here yet. Well, suit is a captured variable, meaning whatever the suit is of that first card it runs into, that's going to be fed into a new variable named suit. This is going to be extremely important in a moment. The other part we have is the strict value of 10 representing the rank, or the first rank that we want. And remember, these cards are sorted, so 10 is going to be the first in there if this is in fact royal flush. Next, we have this strange caret symbol with the same variable name. This is a very interesting part of pattern matching, and a very powerful one, called a pin operator. And it can be used on any variable to make sure the pattern match does not assign over it. If you happen to use the same variable name as something above, that's not going to compare against a value, that's going to assign over that value and shadow it. And that's going to happen outside the context as well of the pattern match. So we want to use pin to make sure it's comparing against the value of that instead of trying to assign it there and just check for the presence. Now, it also means we can capture the suit once and ensure that any pinned mention afterwards happens to be the exact same suit. If it were spades, like our commented example up above, the next card would be expected to be a spade as well as have the rank of jack. From there, we can fill in the rest of the expected cards. Now, let's test that out. Testing it against our string, we find out that that is indeed a royal flush, and you can test this yourself using some of the example code. Now, next, that brings us to a straight flush. A straight flush is both a straight, meaning all cards are one rank apart, and a flush, meaning all of which are the same suit. But it's not quite a royal flush because it's not 10 to ace. It could be 9 all the way up to king, and that would be rather disappointing. Now, going back to our hand, we want to start with an example here, which would be that exact 9 to king with all spades there. We want to define a method to check for a straight flush. Now, this one is rather boring. We're just checking if it happens to be a straight and a flush. Now, nothing says we need to always use new code. We're using other parts perfectly fine. We'll be getting to both of these in a moment. So if we were to test that code, assuming these two functions are finished, we'd find that it also returns true. Next up is 4 of a kind. Now, just like the name implies, this means 4 of the same ranked card. Going back to our hand, we'll start with an example of 4 aces. Ace of spades, diamonds, hearts, and clubs. And define a predicate method, and then match against all of our cards. Now, this one is interesting because it has something new here. We have 2 asterisks on either side of whatever is going to be in the middle of our pattern. This is called a find pattern, another experimental feature which says the pattern can be at any position in the array, either the front, the back, maybe the middle, who knows. In the case of 4, it has to be the front or the back. But this means find this somewhere in this array, as long as they retain the same order. Our 4 cards could be at the front, the back, who knows, but this can handle both of those cases. Next, we want to capture the rank. You might also notice the underscore here, which, as mentioned earlier, is a placeholder for any value, but we don't care to save it as name. We just want to know it's there. Next, we're going to pin rank, much as we did with the last few examples, meaning we expect 4 cards of the same rank, or 4 of a kind. Now, if we were to test that using our example, we can see this does indeed work. Next, we have a full house. A full house is interesting that it has 3 of one rank and 2 of another. Going back to our hand, we'll start with an example of 3 aces and 2 kings. Now let's start with a full house method here and match it against a pattern. Now we can very well have multiple named captures and pins. For the first pair of 2 cards, we want to capture their rank. Now remember, these are sorted, so this does in fact work. And for the case of the second 3, we want to capture that rank as well, but it should be distinct from the first rank, giving us something like this, but something is off. That's 2/3. We have a 3/2 there. That presents an interesting thing in which we have more than one applicable pattern. You might notice that my code here has return true if cards in, which implies there is in fact another pattern. In this case, there's a second pattern that's right below this one in the example code, which has a 3/2. So we're going to need to match against both of these. There may be a way to hack this with an OR conditional, but that would make quite a mess, so 2 captures it is. Now back to the examples. If we were to test this, we can see that we do indeed have a full house. Next, we have a flush, or all cards of the same suit. Back to our hand, we can have an example of a flush in which we have a 2, 4, 6, 8, and 10. So they are in order, but they're still not a straight. They are the same suit though, so we know we have a flush. Now we're going to want to start again by defining a flush method and matching against the cards. Now, much like 4 of a kind and royal flush, we're going to want to capture the suit and make sure that that happens to be the same by capturing the first suit that we run into and pinning the rest. Then we want to test that. And we find out that our example is indeed a flush. Next, we have a straight, or all cards in ascending rank. But to start out with, we want to know what the next card in the sequence is to see if it constitutes a straight. So this one's a bit more complicated. Let's start by upranking a card and going back to our card. Now we want a class method to allow us to add 1 or n to any rank. Typically this is just 1 for basics, but we are going to want to add more than just 1 here. If we were to use that as an example for add rank, we could add 1 to king and get back an ace. Now back to our hand. Let's take an example of straight. Notice the suits are very different, making this different from a straight flush in that we have heart, spade, diamond, club, and diamond. But you'll notice 2, 3, 4, 5, 6. We're going to start by defining a straight method, and then we're going to match against the cards. Now, in the first case, we have something which is very familiar. We don't care about the suit exactly, but we do care about the rank. But how exactly do we see if they're increasing by 1? Well, currently we have to hack this a bit with string interpolation to add a certain number to each rank, or making sure they're all in sequences. I'm not 100% a fan of this, but I don't feel too terrible about this as there is a proposal out for a new expression syntax. This expression syntax will end up looking something like this, which is caret followed by parentheses, and whatever's inside those parentheses will be evaluated as an expression. Now, this has been approved and merged, so patches in the meantime aren't terrible just to test things out, but I would not put them into production either. Remember, pattern matching currently will not allow expressions, hence all the syntax errors you'll probably encounter while testing some things, and hence why the expressions were added for intuitiveness. Now, that's done to try and ensure a complete match, as well as making pattern matching substantially faster. So use expressions sparingly because it does slow things down quite a bit. Do note, it's not yet deployed much outside of some nightly builds. So anyways, back to examples. We can see that our example is indeed a straight. So next we have 3 of a kind, which is very similar to 4, except it just has 3 this time. Back to our hand, we want an example of, say, 3 aces, and a method to go with. We match against the cards, and like 4 of a kind, it could be in the front or back, or in this case, it could be even in the middle. So we want to use a find pattern again and pin the rank otherwise to make sure 3 cards at least have the same rank. And testing it, we find out that that does indeed work. The next is 2 pairs, and as the name suggests, are 2 pairs of the same ranked card. Going back to our hand, we want to start with an example of 2 aces and 2 kings, and define a method to match. Now, matching against the cards in our hand, we're going to want to see that it's very similar to 3 and 4 of a kind, and that we use a find pattern to allow pairs to be anywhere in a list, and similar to Full House in that we have 2 ranks to watch, but there's an issue here. Can you spot it? Let's give that a few seconds. Now, unlike a Full House, 4 of a kind, or 3 of a kind, there's nothing to say that we might not have something like 2 5s, 1 6 in the middle, and 2 7s, meaning that this wouldn't work, except for most of the cases, which is why this is another case where we're going to have 2 patterns, and you'll find that in the example code. So we can add a second case below to it, capturing the middle just to be safe. Now that brings us to testing. And we do indeed have 2 pairs here. So that brings us to our last patterned hand, a single pair. It's like 2 pairs, but only 1 this round. So going back to our hand and getting our example, we have 2 aces here. We're going to want to define our predicate method and test against all the cards to make sure that somewhere in there, they're the same 2 ranks. Now this one is fairly easy after seeing the other examples, and there's not much to it. Now testing it will return that we do indeed have 1 pair here. Now that brings us to the fun part, scoring a game. We have most of the foundation already here to do this, making the final methods, tying them all together, just all the more satisfying to finally get to bring all those little parts of code and finally see them unify into something useful. Now let's go back to our hand and how it should also know how to score itself. Now remember, we had scores earlier as a constant. Now we can use them in conjunction with all of our predicate methods to go right down that list of most specific condition to least, allowing us to see what type of hand we have. If nothing else matches, we go to the highest card in the hand or high card as the base of the score as an alternate. Now, granted, this isn't 100% how you should score a hand, but a particularly intrepid coder might try and implement comparable on a hand to take into account the rank as well as find which hand might be larger between 2 of them. Consider that a challenge, as this talk is already veering a little bit long. Now we can run some of these examples to see how well our code might work. Now remember our constant for examples to run against. They're about to become really, really useful here. We iterate over all of them and see whether or not they're correct. Granted, not our spec or mini test, but those don't fit well on a slide, so here we are. Now the original code has more than a few rows of final output, hence the here doc here, but condensed for the sake of presentation and output. We care about the hand, what its score is, whether or not it's the right score, and what type of hand it was. Running it will give us the correct answers, so congratulations, we solved a good portion of poker with pattern matching. Now, pattern matching is quite a useful feature, and we haven't really begun to scratch the surface of what's possible in it as a new way of thinking Ruby. This is but one of an untold amount of possibilities, and hopefully this talk inspired you to try out a few of your own ideas. I could see all types of uses in things like, say, Rack, or perhaps Rails, or maybe GraphQL, or who knows what else. There are a lot of possibilities out there, and I'd love to see what you come up with as far as using them. If you want to read more of my work or find the examples from this talk, feel free to follow me or reach out to me on any of these social networks. Now, pattern matching was quite an effort between a lot of folks, Sujimoto, Nobu, Zverok, and a whole bunch of other Rubyists contributed a lot of thoughts and ideas, documentation, and had a lot of discussion, pushing the boundaries of what's possible to get us to where we are today. I'm excited to see where we go next, but I believe that Sujimoto has given us a very nice foundation to build upon, and I'm excited to see where we can build from there. Well, it's been fun, but that's all I have for today. Thank you for your time.